So we're going to introduce the concept of an alpha complex. Um, and if you will, the alpha complex is a means of combining sort of two properties which we've seen before. It's like one of which coming from the Delaunay complex and the other one coming from um, the Čech complex. So let's try to give you a sense as to what I mean by that. So you note that for the Čech complex, right, there's this idea of a sort of a length parameter, right? Okay, and so that allows you to, in some sense, it's like, it's like smoothly, well, not smoothly interpolated, but it allows you to sort of, think of a sequence of complexes. It's like which on one extreme corresponds just to a set of points which are disjoint, and the other extreme like corresponds to a situation where you just have one extremely high dimensional simplex where every single point in the point set is connected to each other. Right, so there's this length parameter, it's like which then becomes something like a tuning parameter, and what we'll see later on in the context of persistent homology is that it then gives you a way of seeing what are the, in some sense, important length scales in the problem. Okay, and the problem, if you will, it's like with this length parameter in the Čech complex construction is that you, even though you're in some sort of finite dimensional space. Well, I mean, it's like if you're, say, in RD, right, you could have a situation in the Čech complex where the simplices in the Čech complex are much higher dimensional than the embedding space RD. Okay. So the other thing which we have, of course, are sort of the Delaunay complexes. So the Delaunay complex has the property that if you have points which are in general position, right, there is a upper bound to how large the dimension of the simplices are, right? So the simplices here, right, have dimension sort of less than equal to D if S is a subset of RD and it is in general position. Okay, and there are, of course, other nice things. It's like about the Delaunay complex, which is that if S is in general position, there's also a geometric realization, right? So if S is in general position, there's also a sort of geometric realization of the complex. Okay, so in particular with the Čech complex, there isn't necessarily no guarantee of geometric realization. In RD. Right, it's of course possible to embed the problem into a much higher dimensional space and achieve a geometric realization. But again, that's not really, it's like what one is trying to do. Okay, so, and then the thing which is missing obviously is that there's no length parameter, right? So no length parameter. So as you might expect then, it's like, it's natural then to think of some combination, it's like of the Čech complex and the Delaunay complex, which we'll call the alpha complex. Okay, and again, the way to sort of think about this is that both the Čech complex and the Delaunay complex are nerves of a set of convex objects, right? So with the Čech complex, you have balls of, centered at a point U of a particular radius, right? Those are the sets, it's like, and then the nerves associated with this induce the Čech complex, right? And then with the Delaunay complex, it's like you have the Voronoi cells, VU, okay? So what's basically going to happen then is that we're going to consider now a new set of convex sets which come from the intersection of these two things, all right? So with the alpha complex, right? We're going to have the property that there will be a geometric realization in RD, that you will have a bound that's like on how large the simplices or how high dimensional the simplices can be, and there will also be a length parameter. So it combines, if you will, the best features of both of these. So it combines the best sort of features of both. Okay, and so again, it's like we're going to introduce, it's like a new sort of set of sets. So we're going to call this RU of R, right? And it's the intersection of the balls of radius R about point U with the Voronoi cell it's like associated with the point U. Okay, so some observations, both this and this are convex, so the intersection is again convex and closed. Okay, so since sort of balls and Voronoi cells, sorry, not necessarily closed, I guess, are convex, but they're convex. Right, then sort of RU is also convex. Okay, right, and actually it's like this whole point about closedness is important, right? Because if you recall, it's like when you have the Voronoi cells, you could have, you know, parts of the Voronoi cell which sort of go out to infinity, and so they're not closed, right? Part of the boundary could be at infinity in some sense. So what happens, of course, is that when you take the intersection, it's like these two things, right? BU is closed, all right, and then VU may not necessarily be closed, but they're both convex. And then what happens is that now the intersection is going to have the property that it's closed as well. Okay, so that's going to be useful because if you recall, it's like you know, having closed and convex sets. It's like turns out to be important with this geometric realization theorem. Okay, so all right. So the point is that any two of these disjoint or they overlap along a common boundary, right, which is again what you want. It's like if you want to have a complex, and then together they cover the entire union. Okay, all right. So the alpha complex then is the nerve of this cover, right? But what we're going to do is that we're going to, you know, it's like when you have this nerve, it's like, you know, think of it as an abstract complex. You want to index it in a certain way, and we have two choices, right? We can, you know, it's like we can, we'll just index it by instead of the sets, we're going to index it by the centers. Okay, so the alpha complex of radius r, right, is just the set of points, or the set of subsets of S, right, with the property that the intersection over U in sigma of RUR, right, is non-empty. Okay, and then RUR again is the intersection. It's like a ball of radius r centered about U with the Voronoi cell associated with the point U. Okay, so so we know that sort of RU, right, is contained in VU. Okay, So what has to happen then is that this alpha complex has to be a subcomplex of the Delaunay complex. Okay, and the reason why I care about this is because we have a result that's like about when you can have a geometric realization of the Delaunay complex. Okay, um, so so then if S is in general position, right, we get a geometric realization of the alpha complex, right? By looking at the convex hull of these sets, basically, sigma, right? Of the sigmas. Okay. So, yeah, so actually, I'm sorry, it's like I wasn't, when I said that the reason why closedness comes in is not because of the geometric realization theorem, but it's because of this nerve theorem, which says that, you know, it's like that the nerve, it's like has the same homotopy type, if you will, it's like as the union, it's like of the sets, right? Okay, all right. Okay, all right. So, so since Ru is also contained in the balls, right? So this also implies that something similar holds, right? That the alpha complex of radius r is contained in the Čech complex of radius r. Okay, and then since Ru is both closed and bounded, RUR is closed. I should say RUR is closed and bounded. Right, we have the nerve theorem, right? And they cover the union. Right, the nerve theorem says that implies that they have the same homotopy type. Okay, so the union of the balls, right, is homotopy equivalent to the alpha complex. Okay, the underlying space of the alpha complex. Okay, all right. Right. So the base. I guess I should also say that you don't really lose anything, if you will. It's like by when you take the union, it's like I guess I should say there's one additional observation. When you take the union, it's like of these RURs, it's like over U in S, it's like that's going to end up being the same as the union of just the balls, right? Okay, and that's more or less because you know, it's like the the Voronoi, it's like cells, it's like will sort of partition up, it's like all of RD, and you sort of don't lose anything at the end when you're taking the union of these spaces. Okay, so the union over U and S of RUR is going to end up being this same union as well. Okay, all right. And again, it's like the advantage of thinking about alpha complexes instead of either the Čech complex on its own or the sort of the Delaunay and Čech complex, right, is that now, unlike the Delaunay complex, there's a length parameter, it's like which you can then vary. But at the same time, it's like you have the, it's like the nice properties, it's like of the Delaunay complex, which is to say that there's a geometric realization, okay, if the points are in general position. And in addition to that, there is a upper bound to how large or how high a dimension it's like the simplices are, and that bound is really just the dimension of the embedding space it's like you're working with. Okay, so let me just stop here for now.